Guys, as part of this talk, we'll be talking about disk management. We'll understand the importance of disk management in operating system, why understanding of operating system is important. Then we'll talk about how data is actually stored in the disk. Then we'll talk about different types of scheduling algorithms, followed by how operating system manage space allocation. Post that, we'll talk about RAID architecture. So let's get started. First, a brief about myself. I am a senior software engineer working at New Full Digital. I started my career as a backend engineer, then I upskilled on DevOps and infrastructure, then upskilled on frontend, and currently I am working in applied AI. So if you guys have any questions regarding any topic or need career guidance, feel free to reach out to me. So let's get started. So first question is, why should we care about operating system? Why do we care, right? So whenever we create any application or deploy any code to production, like on cloud or on Docker, right, it will always be running on an operating system. So having an underlying knowledge about how operating system works will give us a leverage compared to others. Whenever we run any program, right, program or application, it will have its processes, threads, it will need memory, and if you are interacting with files, you will need access to file system, right? So all this is handled by operating system. We just call the method like fscan, open, other things, and we rarely care about the underlying abstraction. So all those things operating system takes care for us. So as part of this topic, we'll be focusing on the storage side of it. So let's get started. So now that we know why we should know about operating system, the other question is why should we care about disk management, right? So the answer to that is data is very important for any application or for any organization, especially right now in the world, right, with AI booming in, right, data is very precious to all organization, and disk management plays a crucial role in it. Whenever we create any application, it will have its database, we want to store any records for authentication and for future references as well. We want to log our files as well, right, what action user is performing. We want to store that. There are other scenarios as well where we want to store files. So that is why we need file systems as well. And once our code is ready, right, we will want to deploy it on servers so that outlying traffic can access it, users from across the world will access it, and we need higher throughput, right, so that we can serve as many requests as possible. So that is where disk management plays a crucial role. We want database, file system, servers, better performance, efficient usage of resources, and we want faster data access so that we can serve all requests as quickly as possible. So now that we know why, let's talk about what exactly is disk management. So disk management is a critical function where the operating system handles and organizes data on secondary storage like hard disk, SSD, pen drive, or anything else, right? So it handles and organizes data. What are the key responsibilities of disk management? First is storing the data, allocating space for new files and fragments, then retrieving those data, right? We want to access the data what we are storing. Whenever we delete our data, right, we want it to be managed as efficiently as possible so that we can create new records when required. And then we want optimized access. We want to access that data as quickly as possible. So all these are the key responsibilities of disk management. It ensures safety, reliability, and efficient storage utilization. So let's cover all the topics one by one. The first topic is how disk data is actually stored in hard disk. So this is a basic structure of disk structure. We have multiple platters. Each platter is divided into multiple tracks, and then each track is further divided into sector. So sectors, right, are the smallest segment within each track, and they are the smallest unit of physical storage on a disk. Typically the size is of 512 bytes. We have read-write head, using which the data is actually read from a sector. This read-write head, they move in parallel, right? So whenever they are pointing to any location, right, that particular position is called a cylinder. So cylinder is nothing but a set of tracks that are at the same radial position across all platters. So for this example, this can be one cylinder, this can be one cylinder, so that is cylinder. We know we have talked about platter, track, sector, cylinder, and the data is written by read-write heads onto sectors. So now that we know how data is actually stored in the disk, let's talk about how data is accessed, right? So this is where disk scheduling comes into picture. On our server, we will have multiple IO requests coming simultaneously, and we want to serve them as quickly as possible and in the most efficient way as possible. We want our algorithm to not be biased. We need the algorithm to be fair, such that all requests are handled appropriately. So the primary objective is minimize the seek times. What is seek time, right? Seek time is the time taken for the disk arm to move from one cylinder to another. Like, as data will be written across different sectors, right, the arm would need to move to that particular location so that the data can be read. So primary objective is minimize seek time, and the other is improve performance. So if we have right disk scheduling algorithm, we will be able to increase our throughput of the server. So let's discuss about various disk scheduling algorithm. First one is very simple, first come first serve. It is a queue based processing, wherein the first request which we get, we will serve that. So if our head is on point 50, we'll move it to the next request. So in this case it was 176, then the next, and so on. This algorithm is fair, like we are not differentiating any request. As in the request is coming, we are moving to that request. But as you can see, we are not optimizing the seek time over here. The head is moving to the location without thinking like, is this the closest path which we should have taken? So it results in higher average seek time. So what should we do, right? So the solution is creating a shortest seek time first. So what this algorithm does is it uses greedy approach. It will pick the request closest to the current head position so that we can optimize for the head movement. So over here our head is at position 50. The closest in this is 41. So head will move to 41, and the next closest is 34, then 11, and so on. So it optimizes the head movement. If it was FCFS, we would have gotten like 510 head movement, but now this is 204. But there is a problem here, right? The requests which are away from the head will receive starvation, like they will be accessed like towards the end, right? So it is not uniform wait time will be there. So far away request may be served if closer ones arrive, right? So this may get starved, and high variance in response time. So this is the limitation of shortest seek time. So how can we improve this further, right? So another solution is we will use something called scan movement. Like we will go in bidirectional scanning so that the algorithm is not biased. We will either move towards the left direction or towards the right direction. If we are at point 50 and if we are going left, we will handle all the requests going to the left. We will reach the end of the disk, then we'll start moving to the opposite direction. We'll start moving to the right. Once we reach the end, then we'll start moving again to the left, serving the request. So this is scan algorithm. It is also like called building elevator, similar to how elevator serves request in one direction before reversing and coming to the bottom. Visualization, easy to implement, no starvation. There are two problems in this algorithm. First is like, even though we had no request towards the end, right, even then the head sort of moved towards the start of the disk, and then it started moving to the opposite direction. So that is one disadvantage. Another disadvantage is the wait time is not uniform for the requests which are in the middle, because if the head is moving to the right again, right, this request are getting served twice and the center ones are being starved. So what can we do to make this uniform wait time? So the algorithm is C-scan if we want uniform wait time for all requests. So it has unidirectional service, like it will only move in one direction. So if it is going right, like 50, then 60, and so on, it serves all the requests, then it will move towards the end, like towards the start for here, like towards the left from 0, then it will start serving the request towards the right again. So this way we ensure that there is no starvation of the request which are at the end, and everyone has uniform wait time. This solves that problem, but we still have one problem, which is if we don't have any requests towards the end, why should we go there, right? We can optimize it further, and what we can do is, like, we can look ahead and just move towards the possible farthest head position where we want to go if there are no requests towards the end. So next algorithm is loop. It is optimization over the scan algorithm. It has intelligent reversal. Reverses at the last request instead of the disk page. So here we had the last request which was at 176. We saw that there are no requests on towards the right. So what we did, we immediately started moving to the left. So we were at 177, no request ahead, we started moving towards the left. We had 141, we handled that, 34, and then 11. There are no requests towards the right, so we'll stop here. So this is an optimization over the scan algorithm. Now similarly we have C look. This is an optimization over the C scan. So over here we will reach towards the end, then we'll skip all the requests towards the left, we'll start again from the left. Notice here that it doesn't go towards the end, which is 0, it went towards the leftmost one, which was 11, and then it started serving the request again. So it has improved efficiency, it is unidirectional, jumps between the first and the last request. Okay, so these are all the algorithms. This scheduling algorithm, this is the comparison. FCFS is simplest, but it is slow. In shortest seek time first, right, it is fast, but there could be starvation towards the request which are like towards the end. Scan is balanced, but there is an extra movement, like we move towards the end of the disk, right? And C scan, we have uniform wait time, but there is the jump cost, right? When we are moving towards the left, we are not serving the requests which are in between. Look is efficient, but it is complex to implement. CLOOK is optimized, but there is more logic, it is complex. So these are all the disk scheduling algorithm. Now let's move to the next part, which is how free space is managed by operating system. So what exactly is free space management or free block management? Whenever we delete any record, right, so those blocks are available for use. Like if we want to create a new file, we can reuse that blocks and allocate memory. So OS need to track care of which files you are deleting and what all blocks are available for use. It has a responsibility that we are not overwriting the data, like we don't overwrite the file which already was written, right? And we have to ensure storage integrity. So these are the responsibility of free block management, and we want to improve, like we need to have an as efficient allocation as possible, minimize search latency. Like if we want to create new blocks, right, we should be able to find very quickly, it shouldn't take like much time. So minimize search latency, optimize this throughput. So this all is covered by free space management. As part of free space management, there are various data structures which operating system can use. First one is bit vector or bitmap. So over here we have a binary representation of disk, and each bit represents a block. If it is set to 0, that means that block is available. If it is set to 1, that means that is allocated and we cannot use it. So in this example, consider we have 16 blocks. So we will have 16-bit bitmap. The 1 is set to 1, that means this block is occupied, this is occupied. This bit is set to 0, that means like we know that which block is exactly free and we can allocate memory if required. So advantages, it is very simple and efficient, highly intuitive, fast free block identification. But disadvantages, memory overhead, we need extra memory for larger disks. It is stored as an array of bits. Bitmap are fundamental technique for speed space tracking. So this is very simple. 0 indicates that the block is free and 1 indicates that it is occupied. So the disadvantage to this is memory overhead, right? So what we can do to improve, we can use linked list to store all free disk blocks together so that we have as optimized space as possible. So consider this example. We have block 2, 5 and 8 which were available. So we will create a linked list. Head will point towards block 2. Then we know that block 5 is available, block 8, 13 and then null. So no extra memory is used. Implementation is simple. But then because as this is linked list, right, we have the disadvantages which comes with linked list. Like traversal becomes slow. Search is difficult because we have to traverse them one by one. So those are the disadvantages of using linked list. What can we do to improve the traversal? What we can do is we can create a grouping. Store multiple free block addresses in a single block. First block will store address of multiple free blocks. Last entry points to another block of address. So what we are doing, we are creating groups. So this is for block 100, this is the group. For 200, this is the group. We have 1, 1, 2, 3, 4. This means that these 4 blocks are available. Then towards the end, right, it points to the next block. So 200, it will point to this. We have 2, 1, 2, 3, 300. The end one will point to the another block of addresses. Advantage is faster than linked list and traversal time is improved because we have block wise grouping. Disadvantage is slightly complex to implement. So grouping sort of improves the efficiency in free space management. Okay, but over here we can have one more optimization, which if we look, right, we know that the next 4 blocks are available. Even then we are storing this data. So next algorithm, which is counting, it is like we can store clusters of free block as a single entry instead of storing them individually. It will track the number of free continuous blocks. So here instead of saying 50, 1, 2, 3, 4, what we'll do is we'll start from 50 and next 5 blocks are available. So this is called counting. Where we can use counting is when the disk is not highly fragmented, like we have continuous blocks of memory which are free. Highly fragmented means that we don't have blocks which are next to each other. Like consider for this example, we had 50 which was free, then 52, then 54. So in that scenario we will be storing 50 count 1, 52 count 1 and so on. So it is not suitable when the disk is highly fragmented. So these are some of the algorithms using which operating system does free space management. Now that we know how free space is managed, let's discuss about the last topic, which is RAID. RAID is very important because as we talked about, data is the heart of any application. We don't want to lose track of data, right? Because if data is lost and someone asks any question, we don't know like where, what happened. We need logs, we need data, and it is very important. So RAID is nothing but redundant array of independent disk. Like we will have multiple disks where we will store the data. So definition wise, a technology that combines multiple physical disk components into one or more logical units. It will help us improve the performance, reliability, and most importantly fault tolerance. So if a disk fails, we have another drive to which we can point to. Data is consistent and available, and we have high performance, which is essential for production grade application. So let's talk about different RAID levels. There are various RAID levels. As part of this session, we'll only cover on 4 RAID levels. RAID 0 is called stripping. Over here we will spread data across multiple disks, which will improve the performance, but data safety is not given. Another one is mirroring, where we'll copy the exact data on 2 or more disks. It is highly safe and reliable, but as we are copying the data in more disks, right, cost will increase. Parity is a balanced approach between stripping and mirroring. Over here we will use stripping, but we will use parity. We will not mirror the exact data, but we will store parity data, using which we can reconstruct the data if any disk is lost. So it provides fault tolerance with efficient space usage. And last is RAID 10. It is a combination of 0 and 1, RAID level 0 and RAID level 1. So it combines mirroring and stripping. It will offer highest performance, highest redundancy for critical data, but the cost will increase because we are mirroring the data. Now let's talk about each RAID level in detail. So as we talked about stripping, right, the core concept is split the data across multiple disks, which will allow blocks to be stored and accessed in parallel for maximum speed. So we are maximizing speed. We are splitting, A1 is here, A2 is there, A3, A4. Advantage, very high optimization, full storage we are using. But disadvantage, if a disk is lost, then data is lost. So it offers best performance, but we have a disadvantage of disk failing. Where this is used, high speed application handling non-critical data, where if a data is lost, we don't usually care. Speed is what we prioritize over safety. Now let's talk about RAID 1, mirroring. Mirroring is when data is very important to us, like we are using critical systems like banking and OS storage. So over here what we do is mirroring, as the name suggests, will copy the exact data in another disk, like A exact data is there. Advantages, it is highly reliable, easy, like recovery is easy. If disk 1 fails, we know that disk 2 exists. If disk 2, then we will have disk 3. Disadvantages, 50% of storage efficiency is lost because we are mirroring the data and it is costly. So this is RAID 1 mirroring, easy to understand. RAID 5 is stripping plus parity. Over here we are not using mirroring, we are using parity bit. So using parity bit, like it is XOR of the data, we will XOR A and B and store it as a parity bit, so that whenever if a data is lost from disk A, we can use parity bit to reconstruct the lost information. Now as we will store parity bit, right, the disadvantage is before we write any data, we have to perform complex parity math and store the data on disk 3. Advantages is good performance, fault tolerance and high efficiency, as over here we are not mirroring the exact data, but rather we are only storing parity data. Primary use case, enterprise environment like server, database, where speed and data are critical. RAID 5 is balanced approach for storage, offering redundancy without the higher cost of RAID 1. On RAID 1 we had higher cost because we were mirroring the exact data. Now let's talk about the last level, which is RAID 10. What is RAID 10 is a combination of RAID 1 plus RAID 0. So over here we will strip the data plus we will mirror the data. The disadvantage is quite clear, right? It is expensive. So in this example we need minimum of 4 disks, 50% capacity is lost overhead because we are using mirroring. Performance will increase because of mirroring. We have 2 copies of the same data. Fault tolerance is high because of mirroring. Primary use case for database server and high IOPS application, and safety is non-negotiable. So these are various RAID levels. This is a comparison matrix which will give us an high level overview. With stripping we have high speed, but safety is not there. If a disk is lost, then we are losing the data. Complexity is low, cost is low. With RAID 1 mirroring, speed is medium, safety is high because we have mirrored the exact data. Complexity is low, cost is high. When we move to parity, right, as we are storing the parity bit, the complexity increases, but overall speed and safety wise it is good. The cost is moderate over here. When we move to RAID 10, the speed is high, as we can see here. The safety also increases because of mirroring. We didn't have safety in stripping. Complexity increases and the cost is very high because now we need 4 disks. So these are various RAID levels using which we can decide like which is best suited for our application, and we can use our RAID level accordingly. So with this, we have completed all the topics for disk management. I would like to share a final thought that, as we discussed in the start, right, a good developer write code, but if you are deeper understanding, right, that is when you will become a great developer who understand how underlyingly it works. So with this, I would like to close our session, and if you guys have any question, feel free to reach out to me on LinkedIn.